Alright guys, we are finally on part D. And we started this problem over here, part A, which you can find video for separately, and the setup is separate. And part B is separate, and C is also separate, and obviously some of our answers from those parts are going to help us here in part D. So if you're confused where any of those parts come from, or those answers come from, the answer is going to be from one of those other parts. So part D says we want to know the horizontal distance delta x from the end of the ramp to where the total mass ends. Now, usually, there we go, this will just be one big path, and so I could usually just do one 2D kinematics problem. The issue is I got this whole collision thing that happened right here at the top, and that's going to kind of mess things up just a little bit. Now, the good news is I can basically just do this in two problems. I can just do the first half. We'll say the delta x on the way up. I guess that could kind of be confusing seeing delta x up, but hopefully you've heard my language and it makes sense for that. And the delta x on the way down, which is basically just a two-dimensional problem. So I'm going to come over here. We're going to scroll down. Now I'm going to remind you of some stuff that we found out in part A, actually. That the velocity in the x, once it leaves the ramp, is, let's see, just right over here. That's that 46.1 that you see there. Let's go ahead, 46.1 meters per second x hat. And the velocity initial in the y was that 14.1 meters per second. Of course, that came off the back that we found that the velocity leaving the ramp was 48.2, and it left at an angle of 17 degrees. So we just did a trig to get those two particular guys right there. Now, in part B, we actually found, to go to the top as opposed to 2.5 seconds later, that we had a delta y of 10.1 meters. So we actually have four variables in this column. Actually, sadly though, it's not the variable that we really need in order to get how far it goes in the x. The main thing we need is time. So let's just go ahead and remind ourselves that acceleration is negative g. And if we're just talking about going up, the velocity final for going up is still that 0 meters per second. And with that, we're going to try to find time. Since I have three variables in the y, I'm just going to go velocity final in the y equals velocity initial in the y plus acceleration times time. This cancels because it's 0. We would subtract velocity initial in the y over, and then divide by a. Of course, looking like it's going to be negative, except once I plug numbers in, that's negative 14.1. I'll put parentheses around that to remind you that the negative came from the algebra, and 14.1 is positive. But acceleration is negative g, which cancels out really nicely. And the time of going up should be, I commented on this earlier, pretty close to 1.41, just a little bit bigger. I got 1.44 seconds. Okay, 1.44 seconds. Now, the velocity in the x should in fact stay the same the entire time. Well, before that collision. So the delta x on the way up is simply going to equal the velocity in the x, 46.1 meters per second, times that 1.44 seconds it takes to get to the top. And we should find that while it is going to the top, it should travel 66.3 meters. Now, does this make sense? Well, it was traveling more in the x than it was in the y. So you'll remember in part B, if you watched that or if you did it yourself, that we calculated it should only change by 10.1 meters in the y, which does make sense because as you can see in the y, it's not going nearly as fast. All right, so what do we have here? We have the delta x to when the collision occurred. And you'll remember if you watched the collision video that we said we're not going to worry about how much displacement this takes place. We're just going to say this next part happens right after that. So the main thing that honestly changes is after the collision, the whole mass was going 37.4 meters to the right. So we can basically treat this like it's a problem where this is going 37.1 meters to the right, and we want to know how far in the x it goes before it hits the ground. Now we can't exactly use this guy right here. You might say, well, we have the velocity speed when it hits the ground, and that is true, we do. The problem is that's not in the x or the y, and since we don't know the angle, we can't exactly do trig on that. But one thing we do know is this guy right here, that the height that that collision took place at was 127 meters. So, come over here, we know that the velocity in the x is, scrolling back up real fast, 37.4 meters to the right. We'll just say it's positive now, meters per second, then we'll go x hat. The velocity in the y at the top should be 0, because it's traveling perfectly horizontally. The acceleration during this time is negative g, and the delta y is negative 127 meters. So once again, I have 3 variables in the y, and we're trying to find time. So that's going to give me delta y equals velocity initial on the y plus, times time. Let's just go back and fix that, so it's a little bit more clear. Not that my handwriting is ever clear here. Plus 1/2 a delta t squared. And if you avoid this guy, because you remember that we did quadratic equation on it a couple times, don't forget that only happens if none of these cancel, which since that is 0, this guy does in fact cancel, and the algebra is not that bad. Multiply 2 on both sides, divide both sides by a, and square root, and that's going to give us time. So this is going to be 2. By the way, you'll notice that delta y is negative, because obviously it's going down this 127 meters. That's 2 times negative 127 meters, all over negative g, square root the whole thing, and the time that it takes to fall is 5.1 seconds, or pretty close to. And once again, you might say, wow, that's a lot of time compared to going up. Well, it had a lot further to fall. It fell 127 meters as opposed to going up 10.1 meters. So it makes sense that it'd take a lot longer. Okay? And we know that it was traveling this far, or that fast in the x, on the way down. So that should just be 37.4 meters per second times 5.1 seconds. I don't think I said this last time, but this, of course, is the constant velocity equation, which we also see over, let's see if I can position this a little bit better for us, over what we did over here, because the velocity is not changing specifically in the x. And that should be, on the way down, multiply that around 190.4. This is the time where I, of course, once again mentioned that if your answers aren't perfectly the same as mine, don't worry about it. I'm saying this on the off chance that this is the only video that you watched, because I definitely commented on it in all the other videos. So, the total displacement from the edge should be the displacement on the way up plus the displacement on the way down. So we'll say, we'll call displacement of, I don't know, total is equal to displacement on the way up plus displacement on the way down, which would be 66.3 that we started off with, plus this 190.4 meters, which gives us roughly a final answer of 256.7. If it makes you feel any better on the rounding thing, when I calculated this in previous years, I think I got like 257.48, and I think that's a little bit more accurate. You'll notice that is also off by less than a meter, but it is off a little bit. So hopefully that makes you feel any better if you're off by about that much. If you have any questions on why you're off or that type of thing, just let me see your work and we can talk about it. And that's how you do number 3.